Greetings. So welcome to today's class. So what we will do is that we will continue our discussion on Bode plots in today's class. So if you recall, in the previous class we were looking at Bode plot, and we recall that the Bode plot has two subplots. One is the magnitude plot, what is also called as the log magnitude plot, wherein we plot the magnitude in decibel measure, which is frequency. The frequency is plotted on a logarithmic scale, and the reason for using a decibel measure for magnitude is that we can break down the magnitude of product of multiple terms into the sum, right? So that's an advantage we have. And the phase plot is something where we plot the phase of the sinusoidal transfer function in degrees, which is omega. Another, once again, the advantage is that when we do that, we can sum the bases of the individual blocks and plot the consolidated phase plot, right, of any given transfer function. So towards that, we asked ourselves the question: what are the typical building blocks, that are used in this regard? So that's where we identified these building blocks, which consists of this gain k, 1 by s and s, 1 by ts plus 1 and ts plus 1, and the second order factors of the form omega n squared divided by s squared plus 2 zeta omega n plus omega squared, and it's reciprocal, right? So those are the terms. Okay, so before going into the Bode plot of the individual factors, let me recap a few fundamental identities from the theory of complex variables. Okay, so this will be helpful going forward. So we have discussed this at many instances. I'm just summarizing what we need. So if you take a complex variable a plus jb, its magnitude is going to be square root of a squared plus b squared, and the phase of a plus jb is going to be equal to the tan inverse of the imaginary component divided by the real component, right? So that's going to be one identity that we will use. And another formula which will be quite helpful is that the product of a plus jb minus a times a minus jb will be a squared plus b squared. Okay, that's another formula. Okay, so and another concept which we have already learned is the following: if any sinusoidal transfer function is of the form n of j omega divided by d of j omega, so then what we have is that the magnitude of the sinusoidal transfer function is going to be the ratio of the two magnitudes, right? N of j omega and d of j omega. That is point number one. And the phase of the sinusoidal transfer function is going to be the difference in the phase, right? We can even write the phase of, there are multiple ways of writing the same thing. One can essentially say the phase of n of j omega plus the phase of 1 by d of j omega. That's the same thing as the phase of n of j omega minus the phase of d of j omega. Okay, so these are some formulae or equations that I just wanted to present, before we went ahead with today's discussion. Okay, so please remember all these equations. We'll be using them as we go along. So in the previous class, we had looked at the Bode plot of this factor k, right? So that was pretty straightforward. Since k is a real number, its magnitude in decibel is going to be 20 logarithm of absolute value of k decibels, and its phase is going to be either 0 degrees or 180 degrees, right? Depending on whether it is a positive number or negative number, right? So that's it. That's pretty straightforward. So now let's go to the other factors. All right. So the second factor that we shall consider is of the form 1 by s. Okay, it's an integrator. So immediately we can rewrite this as d of j omega is 1 by j omega, right? And if we multiply and divide by the complex index j, we will get that minus j by omega, right? Because j squared is minus 1, right? So this will be the what is it, factor, right? So immediately we can observe that this is going to be on the negative real axis, right? If we plot it on the complex plane. Why? Because there is no real component, and the imaginary component is going to be always negative, right? Because omega is going to be positive, right? If we look at omega as angular frequency, we are going to have a positive number. So this is going to be on the imaginary, right? So if we were to take the magnitude of this factor, we will just get 1 by omega, right? Because that's going to be the magnitude. So all of us can immediately observe that. And if we want to write it in terms of decibels, as we discussed, we just take the logarithm to the base of the absolute value, right? And multiply it by 20. So we can immediately say that this is going to be minus 20, right? In decibels. Okay, so please note that log of 1 by what to say, some more identities which we can which we will essentially use is log of AB is going to be equal to log of A plus log of B, right? And we can also say log of A divided by B is going to be equal to log of A plus log of 1 by B, and log of 1 by B is minus log B. Okay, so those are all for identities that we are using here. So, okay, so that's, I'm sure all of us recall these equations, right? So, and this writing down, right? So this is what we have. So, and as I discussed, if we were to plot the what to say, evolution of this, okay, in a complex plane, what we call as dj omega plane. Okay, so because this is indicator of this factor d of j omega, immediately we can see that this along this negative real axis, sorry, negative imaginary axis, right, as omega is there. Okay, so consequently its phase, we can say that it's always going to be on the negative real axis. So the phase is going to be either plus 270 degrees or minus 90 degrees. Okay, so depending on how we want to look at it. Okay, so consequently we shall what to say, write the phase of this thing as minus 90. Okay, so that's what we will consider. All right. Okay. So now, having looked at the magnitude and phase, we are going to essentially look at the magnitude a little bit closer. So let's look at the expression for the magnitude, okay, in decibels. Let's say we want to figure out what will be the magnitude at 10 times omega. So we use the same magnitude expression, and we want to go from omega to 10 times omega, that is 1 decade above, right? So as we know, this is going to be log of A times log of B, right? So that's how we can write the product, a logarithm of the product 10 omega. So log of A times B is log of A plus log of B. So log of 10 omega will be equal to log of 10 plus log of omega, right? So that's what we will have. And as we know, log of 10 is 1, so we'll get minus 20. And then we'll get minus 20 log of omega, right? So we can immediately observe that as we go from omega to 10 omega, there is a reduction of minus or reduction of 20 decibels, right? So we can essentially say that as frequency is increased by a decade, what do we mean by a decade? That is going from omega to 10 omega, right? the magnitude reduces by 20 decibels. Right? Magnitude reduces by 20 decibels. So when we plot the magnitude plot on a what to say for this particular factor on a scale that uses a logarithmic scale for frequency, let's see what happens. Okay, so let me plot the magnitude plot, okay, of this factor d of j omega in decibels. Okay, this is frequency using a logarithmic scale. Let me take some particular values of frequencies. Okay, it will become clear as to why I am choosing them. So let's say we choose the frequency of 1, 10, and 0.1. Okay, so let me say we choose these three frequencies. We can immediately see that since we are using a logarithmic scale, so we can essentially observe that the gap between 0.1 and 1 is equal to gap between 1 and 10. All right, so please remember that, right? So now, if we want to essentially plot or calculate the magnitude of this factor, right? So d of j omega in decibels. Okay, in this case, it's in this particular case, it is minus 20 log of omega. Please note that, as I mentioned in the previous session, right? So from here onwards, when we talk about logarithm in this discussion, we are going to use logarithm to the base 10 by default, right? So if you have these three frequencies, right, 0.1, 1 and 10, right? So what will be the corresponding values? Let's say we take 0.1 first. What will be minus 20 log of 0.1? What is going to be log of 0.1?
Minus 1.
It is going to be minus 1, right? How did I get it? So we can say logarithm of 0.1. We can write it as logarithm of 10 power minus 1, right?
Yes.
And when we take the logarithm to the base 10, we get minus 1, right? So then we might multiply by 20, minus 20, so we'll get plus 20 decibels, right? I hope it's clear how we got plus 20, right? Okay. So then, if we look at, please stop me whenever there are questions, okay? So I'm just explaining the steps, but if you have any questions, please feel free to stop, okay, whenever necessary. So now if I substitute omega equal to 1, log of 1 is going to be 0, so 20 log 1, you'll get the 0 decibel. So that's what will happen. Now, what will happen to log of 10 at omega? I hope it's clear how we got 0, right? Because log of 1 is 0. What will happen to log of 10?
Minus 20.
Minus 20.
Very good. Log of 10 will be 1. So then we multiply by minus 20, we are going to get minus 20, right? So let's plot them. So let us say this is 20. Let's say this is the 0 decibel marker and this is the minus 20. Okay, they are equally spaced, obviously, right? So now if I were to mark them, so this will be 20 decibels at 0.1, 0 at 1, and minus 20 at 10. We can see that the magnitude plot of this factor 1 by s, sorry, not a perfectly straight line, but then you can get that, right? So get the point, right? So this is going to be a straight line, right? I have tried to draw a straight line. In reality, it is a straight line, and its slope is going to be minus 20 decibels per decade. Okay, this is the slope of the magnitude plot of 1 by s. Okay, or log magnitude plot of 1 by s. All right. So, how did we write the slope to be minus 20 by decibels per decade from the analysis that we just did, right? So when we went from omega to 10 omega, we saw that the value reduced by 20, right? So that's what used, right, to essentially write. Okay, so we can immediately see that this is the what to say magnitude plot, okay, of 1 by s. So now, if I want to draw the phase plot, what will I have? I essentially do the same thing. That is, I now go and draw another curve wherein we plot the phase of d of j omega in degrees. This is omega. Okay. So once again, we use the same scale, 1, 10, and 0.1. We already observed that the phase is going to be minus 90 degrees. Okay? So let's say this is 0 degrees, this is plus 90, this is 0, and this is minus 90 degrees. Okay, so the phase curve is going to be a horizontal line. Okay, this is going to be at minus 90. So this is the phase curve of the factor 1. All right, so I'm just marking it there. Okay. So I hope it is clear how we obtain the magnitude and phase plot of the factor 1 by. All right. Okay. So any questions on that?
So can you explain like how we get minus 90 phase for this?
Minus 90, because we can immediately observe that if we go here, right? So please observe that the term is minus j by omega. So any variable will have a what to say, a real part and the imaginary part, right? Any complex variable. We can observe that immediately as far as the sinusoidal transfer function corresponding to 1 by s is concerned. It only has an imaginary part, right? The real part is 0. So, and the imaginary part is always minus 1 by omega, right? So, we can rewrite this as, this is nothing but j times minus 1 by omega, right? So, we can immediately observe that this imaginary part is going to lie on the negative imaginary axis, right? For all positive omega. And for any point that lies on the negative imaginary axis, the phase or angle can be considered as minus 90 or plus 270. Correct? So that is what we are having. I hope that is clear. There is a reason why we are choosing it as minus 90 and rather than plus 270. That will become clear as we go. Okay? Is that clear?
Yes, Professor.
Okay. So please note, just to further clarify the question, please recall the sign convention followed for angles. Okay, so as far as this complex plane is concerned, a angle is considered to be positive when measured counterclockwise from the positive real axis. That is why this angle becomes positive, right? Because we are going counterclockwise from the positive real axis. This angle becomes negative because we are going clockwise from the positive real axis. Sorry. That's how we design the sign convention.
Professor, one general question. On the same lines, when we have an imaginary, then we'll have minus 90. So, right. We have j, only the imaginary part, j of minus 1 by omega. So all values lie on the negative imaginary part. So when will we have some positive imaginary points?
Okay. We are going to come to that shortly. Okay. Yeah. So that's the next factor we are going to look at. So I'm going to immediately answer this question by considering the third factor. So what is the third factor that we are considering? If you recall, the third factor that we are considering is the derivative block, right? Is it not? So if we consider the third factor, okay, looking at how I wrote the factors, okay, I'm using D of, right? So the third factor that we are going to consider is D of S. Okay, so D of S is yes, right? So now if we substitute D of S, sorry, S equals j omega, I have only j omega, right? And then this implies that the magnitude of D of j omega is going to be equal to 20 log omega decibels, right? Because the magnitude is only going to be omega. Okay, and if I take it in decibel measures, it is going to come as 20 log omega decibels. And the phase, what do you think will be the phase now? Right? So its phase will be the following, right? So if I go here, you can immediately see that I am going to have all the values on the positive imaginary axis, right? So that angle is going to be plus 90, right? So the phase is going to be plus 90. So I hope that answers your question, right? So you're asking whether we were going to have terms on the positive imaginary axis. So you can immediately see that for a derivative term, we are always going to have the points on the positive axis. Does that answer your question, Sri?
But previously, for any imaginary value which is having minus, okay, as the value minus is there, it will come on the negative side. That's what you meant. For
Yeah, because
omega.
this is the negative imaginary axis, right? This is
Right.
the positive imaginary axis. Correct? Is it not? So since there is a minus sign here, that's why it goes in the negative.
Okay,
Right?
okay. Now understood. Yeah.
Right? So in our case, what we just saw, it is plus j omega, right? So it becomes positive, right? And the positive imaginary axis, right?
Yes, Professor. Understood.
Okay? Yeah.
Yeah. Yeah.
So the phase becomes 90 degrees. I hope it's clear how we got the magnitude to be plus 20 log omega decibels. So what can we conclude about the magnitude plot? So I am just going to go and plot here, right? So, hello? I think someone, Ramkumar, do you have a question? Okay, so essentially, if we have this second, let's say, factor, which is 20 log omega, right? So what do you think will happen if we write a similar table at 0.1, 1, and 10? Can you tell me the values? What will be the value at 0.1?
20 decibel.
Uh, uh, Now it's 20 log omega, right?
20.
It will be minus 20,
Minus
right?
yes,
Yeah,
yes.
correct. So because you take log of 0.1 will be minus 1. So now there is no minus 20 to multiply with, right? It's plus 20. So 20 multiplied by minus 1 will be minus 20. Log of 1 will be 0, and the 10, what will you get?
20.
20.
We will get 20. Very good. Okay, so you can immediately see that we are sort of going to have a mirror image, right? So these are going to be the 3 points for this factor, and consequently, the magnitude plot of f is going to be a straight line. This is for the factor s, right? It's going to be a straight line with a slope of plus 20 decibels per decade. I hope it is clear how we got this magnitude, right? So this is for 1 by s, that's for. All right. So you can immediately see that, like there's sort of some symmetry because the magnitude plot is a mirror image about that 1, 0 point, right? As far as the magnitude plot, log magnitude plot is concerned, right? So you can see some symmetry, like between a factor and its reciprocal, right? When we are writing this, drawing this log magnitude plot. Now, looking at the phase curve, it is going to be a plus 90, right? It's going to be a constant line, and that's going to be a plus. So these are the magnitude and phase plots of the factor f, which is the derivative. All right. So I hope this exercise is clear. How we got what to say, the magnitude plot and the phase plot of the factor f. All right. So now we go and look at 1 by ts. Okay. Any questions? Hello. So let's go ahead and look at the factor 1 by ts plus 1. So if this is a first order factor, so immediately the corresponding sinusoidal transfer function will be 1 divided by t times j omega plus 1, because we just substitute s equals j omega, right? Wherever there is s, we substitute j omega. Okay, so this is what we have. So now this can be rewritten as 1 divided by 1 plus jt omega multiplied by 1 minus j omega. We just multiply with a complex conjugate. This is what we would have. So if we, as we just recap, a plus bj minus times a minus bj will be a squared plus b squared, right? So when we multiply with the complex conjugate, the denominator becomes 1 plus t square omega square. I'm sure that is clear to all. And I can split as the real and the imaginary part in this way. Okay, I'm just doing it for demonstration. So this is what we have. Sorry. Okay, so this will be the real part and the imaginary part of this particular factor, right? 1 by TS. Okay, now if we look at this magnitude, what do you think will be the magnitude? Magnitude of this d of j omega. So we can just straight away write from this, right? So we don't need to take the square of the real part and the square of the imaginary part, add them, and then take the square root. We can straight away write from this simplification, which you already know. That's going to be the ratio of the magnitude of the numerator, which will be 1. The ratio of the denominator magnitude is going to be t square root of t squared omega squared plus 1, right? Because that's something which all of us will know, right? So then the phase of d of j omega, once again we can take get it by finding the phase of 1 and the phase of t of j omega plus 1. The phase of 1 is 0. The phase of t of j omega plus 1 is going to be tan inverse of imaginary by real part. Imaginary part is t omega, real part is 1, sorry. So we get tan inverse of t omega. So the net result is minus tan inverse of t omega. Okay, so that's what we have. All right. Okay. So I hope it is clear how we got the magnitude and the phase, right? So what did we use? We just used this formula that we looked at initially, right? So you recall this, right? So when we had a function which is the ratio of two factors, an easier way to write the magnitude and phase would be to take the ratio of the individual magnitudes and also the algebraic sum of the individual phases. That's it. Like that will help us, right, and make things easy. So that's what we have done. So consequently, we get this. Now, what happens? Like let's analyze this magnitude a little bit more. So if you want to look at the magnitude and decibels, we take 20 log 10, the magnitude, which will be square root of 1 by square root of 1 plus t square omega square. This can be rewritten as minus 20 log of square root of 1 plus t square omega square decibels. Alright, so this is the magnitude of this factor in decibel measure. Alright, so I hope it is clear, right? So what we mean by decibel measure. Okay. So now, if we were to analyze this a little bit more, right? So if we look at low frequency, so what do I mean by low frequency? Let me do this, and then it will become clear to all of us. So let us say when frequencies are lower than 1 by capital. Okay, implicitly we are considering t to be positive, right? So let's look at what happens when we have pretty low frequency. So when omega is very much less than 1 by t, we can see that t omega is very much less than 1, right? By taking t to the other side. So let us say t omega is 10 power minus 2, right? So what can we say about 1 plus t squared omega squared? What will be an approximation of this? So let's say t omega is 10 power minus 2. The square of that is going to be 10 power minus 4. Let's say you add 1 to 10 power minus 4. What will be the result?
Close to 1.
It is going to be close to 1, right? So you can immediately see that at low frequency, like we can approximate 1 plus t squared omega squared to be 1 itself, right? So then what we may have is the following: the magnitude of the factor d of j omega, which is going to be equal to minus 20 log to the base 10 square root of 1 plus t squared omega squared decibel. That's going to closely become minus 20 log 1 decibel, which is nothing but 0 decibel, right? So I hope it's clear how we got this, right? And this is what is called as a low frequency asymptote. See, as we have already looked at what is an asymptote indicates a trajectory to which a curve will tend to, right, under some condition. So we can immediately see that what it means is that the magnitude of this term, magnitude of this term under study tends to 0 decibels, okay, as omega tends to. Okay, so that's why it's called as a low frequency. I hope it is clear why it is called as low frequency asymptote. All right. Okay. So now, going forward, at high frequencies, what do you think will happen? Let's say we go to higher frequency. So wherein omega is much bigger than 1 by t. Okay. So if the frequency is high, t omega is going to be much greater than 1. Okay. Then what will happen to 1 plus t squared omega squared? Is going to be approximately equal to, let's say t omega is 10 square, 10 power 2. T squared omega squared will be 10 power 4. So you add 1 to 10 power 4. What is the approximate value?
10 power 4.
10 power 4 itself, right? So this will tend to t squared omega squared, right? I hope it is clear, right? What we have here. So then the magnitude of this factor d of j omega will be minus 20 log to the base 10 square root of 1 plus t square omega square. This will approximately become minus 20 log to the base 10, okay, square root of t square omega square. This will be minus 20 log to the base 10 t omega. Okay, so this is going to be what is called as a high frequency. Why is it called high frequency asymptote? Because as omega tends to higher and higher frequencies, this is the value to which the magnitude of this particular factor will tend to, right? So that's why it's called as a high frequency asymptote. All right. Okay. So immediately we can see that this high frequency asymptote is a straight line with a slope of minus 20 decibels per decade, right? So this high frequency asymptote is a straight line with a slope of minus 20 decibels per decade. How did I state this? Can you reason out how I stated that the slope of the high frequency asymptote will be minus 20 decibels per decade? So just use the same logic which I used some time back, right? So let us say we go from omega to 10 omega. So what do you think will happen? We'll have minus 20 log 10 times t omega, right? Minus 20 log 10 times t omega is going to be minus 20 log 10 plus log t omega, right? So is it not And immediately we can say it is going to be minus 20 log t, right? So immediately you get the idea as to how we got the slope to be minus 20 decibels per decade, right? Is it not? Because we are reducing by 20 decibels when the frequency is increased by a decade. Correct? Yeah. I hope it is clear, right? How we got, right? This is how we evaluate the slope also. All right. So, any questions on this? So, if we were to plot the asymptote, this is what we are going to do. Okay. So, let me plot the asymptote. Right. So, we will plot omega. I am going to use a slightly different scale now. I'm going to say we will take omega to be 1 by t, let's say 10 by t, and let's say 0.1. Okay, so what we are going to have is the following. At low frequency, okay, so we are going to, okay, so I need to essentially write what I am plotting. So I am plotting the magnitude of this factor in decibels. Okay, and let me put a scale also. Let us say this is 0 decibels, and let us say this is minus 20 decibels. Okay, so let's use it. So now at low frequencies, what I'm going to have is that like I'm going to have 0 decibels as the asymptote. So if I draw this blue dashed line, okay, I am essentially plotting the low frequency. I'm just exaggerating and extending it just to show that I am drawing the low frequency asymptote. All right. So now, if I want to draw the high frequency asymptote, I need to draw minus 20 log t of omega, right? So when if I want to draw minus t log t 20 t omega, so let us say in decibels. Suppose if omega equals to 1, what will be this measure minus 20 log t omega? If you substitute, sorry, omega equals 1 by t, sorry, not 1. Okay, if you substitute omega equals 1 by t, what do you think will be minus 20 log omega?
0.
It will be 0 decibels, right? Because t omega will become 1, log of 1 will be 0, right? Correct. So now if I substitute omega equals 10 by t, what will I get?
Minus 20.
I will get minus 20, right? Of course, this is in decibels. We need to write the units, right? So for the high frequency asymptote, at 1 by t, we have 0. At 10 by t, we have minus 20. So we can immediately say that the high frequency asymptote will be a straight line that will pass through these points, and it will have a slope of minus 20 decibels per decade. Okay, so this will have a slope of minus 20 decibels per decade, and this is the high frequency asymptote. Okay, and you can immediately see that both the high frequency and the low frequency asymptote intersect at the frequency 1 by t. Okay, and this 1 by t is what is called as a corner frequency. Okay, so the corner or the break frequency is the frequency at which the two asymptotes intersect. The low frequency asymptote and the high frequency asymptote intersect each other, right? The low frequency and the high frequency asymptote intersect. Okay, so in this case, omega is corner frequency is 1 by t. Okay, in this case, okay, it is 1 by t, radians, of course. All right, so 1 by t is the corner frequency for this particular case. All right, So this is the what I say. We have not completed the magnitude plot. This is the what to say, the asymptotes, right, or the asymptotic plot. Okay, as far as this plot, this what to say, factor 1 by Ts plus 1 is concerned. Now, in fact, if you look at this 20 log T omega, some people will say that it has a slope of 6 decibels per octave. Why do they tell like that? Because immediately, if you observe that, like if we look at this plot and we go to two times this factor, we go to 2 times T omega, okay? From a frequency, we go to twice the frequency. What are we going to get? We will get 20 log 2 minus 20 log T omega. And can you calculate what is 20 log 2? Please do logarithm of 2 multiplied by minus 20 and tell me. What will you have?
(6.02).
6.02. So we take, we take 2 logarithm and then like we multiply by, of course, minus 20. So it will, you'll get minus 6.02, right, as you can readily observe. So let's approximate it as minus 6. Of course, if you want to be very accurate, we call it minus 6.02, then minus 20 log T omega. So for that reason, people will say this high frequency asymptote has a slope of minus 6 decibels per octave. So these are two different units for indicating the slope of the asymptote. Okay, so they mean the same. One can say the slope is minus 20 decibels per decade, or people will say the slope is minus 6 decibels per octave. All right. So I hope the equivalence is clear, right? Why people call it in both units. Okay. What is the value in both units? Right. Okay. So now, what we are going to do, right? I'm going to leave you with a question and an exercise to think of. Right. The question is, okay, we have plotted the magnitude curve in terms of asymptote, right? So what is the actual magnitude plot of 1 by Ts plus? So what I want you to do is to try out this exercise. Okay, I'm going to leave you with a table which you have to fill in. Okay, and then we will discuss this tomorrow. Okay, so let us say we construct a table wherein we have omega, right? And then we have the magnitude of this factor in decibels, okay? And we have the asymptotic magnitude. Let me call it as m of j omega asymptotic, okay, in decibels, okay? And the error between the two, okay, which will be the difference between the actual and the asymptotic value, right? So what do I mean by the actual magnitude? The actual magnitude, as we know, is going to be 20 log to the base 10 square root of what to say, 1 plus t squared omega square. Okay, so the asymptotic magnitude is either 0 decibels or minus 20 log T omega, right? Depending on whether the frequency is what to say, less than 1 by T or greater than 1 by T. Okay, so this is going to be there are going to be 2. It is going to be 0 decibels when omega is very small than 1 by T. It is going to be minus 20 log T omega when omega is very large compared to 1 by T. Okay, which is the corner frequency. So what I want you to do is essentially construct this table for various frequencies. Okay, so as an intermediate point, let me take the corner frequency. Okay, you go one decade above the corner frequency, which will be 0.1 by t, and one decade below the corner frequency, which will be 10 by t. You also go one octave above the corner frequency, which will be 0.5 by t. One octave below the corner frequency, which will be 0.5 by t. I'm sorry, I think I told the term is the reverse order. Let me clarify. Let's say 1 by t is the corner frequency. You go one decade below the corner frequency, you'll get 0.1 by t. We go one decade above the corner frequency, you'll get 10 by t. You will get, if you go one octave below corner frequency, we get 0.5 by t. We go one octave above 1 by t, we get 2 by t. Right? So these are the 5 frequencies for which I just want you to calculate the value. Please calculate these numbers, right, by substituting in these equations, and then like we will observe, right, what is going to be the actual magnitude value vis-a-vis what we get from the asymptotic equation, right, asymptotic magnitude. Okay. Then we will also figure out, like what is the difference between the two, right? So if you are going to look at the asymptotes and the actual value. All right. So I leave you with this exercise, and then like we will continue from here in the next class. So any questions on this?
Professor,
Yes, please.
this factor 2 and 3, why should not select 270 degree for phase calculation? Why we should select, factor 2 and 3?
Factor 2 and 3, y minus 90 and plus 90, right?
Yes, yes.
Right, is it not? So we will most likely discuss it 2 to 3 classes down the line. Okay, yeah. All right. So that's a good question. So if we go here, as we discussed, let me go to the correct plot. Okay. So let's say we look at the factor minus 1 by s. Sorry, 1 by s. Sorry, there's some problem. So suppose this. Yeah. So if we look at this plot, like I mentioned that, if we consider the factor 1 by s, the phase can be, if you look at it, the point will lie on the negative imaginary axis. So the angle could be thought of at either plus 270 degrees or minus 90 degrees. Why did we choose minus 90? Similarly, if we have the factor s, the point will lie on the positive imaginary axis for all omega, right? Then why do we take it as plus 90 degrees? Why not minus 270 degrees? We will find the answer, okay, like as we go along. Okay, so there is a physical connotation to that, which we will discuss maybe 2 to 3 lectures down the line. All right.
Okay.
Yeah, sure. All right. Any other questions? So if not, let me close today's session. We will continue in the next session. Thank you.